Okay, so please confirm that you can see this iPad screen, yes?
Yeah.
Okay, good, thank you. So, if you remember, we start graph theory, which I would say is an interesting topic in mathematics in its own. And now we solved some problems. If you remember, yes, we continued up to here. So this is from the previous lesson. Hopefully you remember. And now I want to continue some examples today. For example, let me just start for warming up. What is the largest size? So do you remember what was the order? Order was the number of vertices and size was the number of edges. Yes? So what is the largest size of a simple graph of order 7? Any ideas? Yeah, please do not write on chat window because I will not be able to see that.
Maybe 7 times 6.
No, 7 times 6.
7 times 6 divided by 2.
Yes, 7 times 6 divided by 2. How did you come to that conclusion? So let me see. You say that the order of the graph is supposed to be 7, and it is mentioned that the graph is a simple graph. Do you remember it? So here, the existence of a loop and the existence of a multiple edge is not allowed. They are not allowed in the simple graph. They are multigraphs. Okay? So here I want to have a graph with the largest possible size, but I want to keep the number of vertices, the order, to be 7. So it means that, yeah, these are just very simple problems you need to convince yourself. So 4, 5, 6, 7. So if I want to maximize the number of edges, it is clear that I need to connect every 2 edges together. But I cannot connect 2 points with more than 1 edge. Okay? If I ask you, by the way, if I ask you what is the largest size of a multigraph of order 7, what would be the answer?
Infinity.
It can go up to infinity because you can just add multiple edges between 2 vertices and then you are increasing the number of edges. Okay, but in the simple graph, I have some limitations. I want to connect every point together. So that's a combinatorial problem, yes? I would say that I want to count in how many ways I can connect 2 points. So in other words, I want to count the number of line segments between all these points. Okay? So that's a combination problem. So that is 7 choose 2. Yes? Why? Because every choice that I make between these points will give me a line segment, and that is a combination problem, not a permutation problem, because there is no difference. If I call this vertex A this B, there is no difference between line segment AB and line segment BA. They are equivalent, so that's not a permutation problem, so that's a combination problem, and that's it. And as you said, if you want to calculate it in any way that you know, this becomes 7 times 6, if you remember, divided by 2 factorial. So the answer would be 21. And that happens if I connect all these points together. Yeah, please interrupt me if you have any questions. I will probably not ask you, do you have questions or not? Number 12. Is there any simple graph of order 8 and size 29? Motivate your answer.
No, there isn't.
Why?
Because if we use the same method as in example 11 to find the largest possible size for a graph with order 8, it becomes 28.
Exactly, thank you. Yes, because the graph is again simple, the maximum possible size of a simple graph of order 8 happens when I start connecting all pair points together. Okay? And if I do this maximally, what I get at most, I would get choose A2, so then it becomes 8 times 7 divided by 2, so it becomes 28. But 29 is greater than 28, so it is not possible. No, so I would say no, there are no. There is no such a graph. A simple graph. Okay, and then you can realize that this is the remark. If I have a simple graph, the number of edges is at most equal to p times p minus 1 divided by 2. That's exactly the same scenario. If I tell you that I have p vertices, what is the what is the largest possible value for the number of edges? You would say that I connect all of them together, so I will have choose p2, so that it becomes p times p minus 1 divided by 2 factorial, which is 2. Yes, so this is the maximum number of edges for a simple graph. As you see, I have written it in red. These are very simple problems, by the way. Show that the relation given in the above remark might not be true for a multigraph. And I think that's also simple. These simple problems helps you to get familiar with the concept, try to feel it. Okay, show that the relation here might not be true. It might be true, of course, but might not be true if I replace a simple graph with a multigraph. Yes, and that is clear. Let us make it as simple as possible. For example, let me take 2 points only, and then if I put 2 there, it becomes 1, and then I have this one. Yes, so this is probably, if I ask you, is this a simple graph, you would say no, because there are more than 1 edges between these 2 vertices. And then if I ask you what is Q, you would say Q is 2 in this problem. What is P? P is 2. So if I calculate P times P minus 1 divided by 2, this becomes 2 times 1 divided by 2, which is 1. And you see that this relation does not hold, because Q is 2, but P times P minus 1 divided by 2 is 1, and 2 cannot be less than equal to 1. That's it. Okay? So if you don't mind, let me just give you a little bit of time, or 2 or 3 minutes at most, so that you can solve this problem. Okay? Your message I cannot see. Sorry, you can just tell to me what is going on. Yes. What did you get?
I think the minimum size is
10. Okay, and what is the minimum order?
Well, I mean,
order means the number of vertices. Don't get confused. Order is related to the number of vertices, and size is related to the number of edges. And then you don't.
The minimum order is 10. Sorry.
Okay, so Q is the size, P is the order. Remember. Okay, let me check. Any other opinions? Okay, so how we should solve this problem? I would say that, okay, this is given to me in the problem that 4p plus 5 is what is less than or equal to q. Yes, this is another way of reading the same inequality. When you say q is greater than 4p minus plus 5, it means 4p plus 5 is less than or equal to q. And by the remark, we learned that q, it should be less than or equal to p minus 1, okay, divided by 2. So if I compare them, it means that 4p plus 5 is less than or equal to p times p minus 1 divided by 2. Yes? And this is an inequality. I have to solve this inequality for p. But of course, p cannot be a negative number, cannot be a half a number. It should be a positive integer, and you know that p cannot be 0. Yes, q can be 0. Let me just remind you, q can be 0. For example, if I draw these 2 dots, what you see is a graph without any edges. So q can be 0, but p cannot be 0, because if you don't have any vertices, you don't have any graph in the first place. But you can have a null graph, a graph with only vertices without any edges. Okay. So let us try to solve this inequality. So for example, I will prefer to multiply both sides by 2, so then it means that 8p plus 10 is less than or equal to. Let me multiply that p also inside. It becomes p squared minus p, and let me move everything to the right hand side. So 0 is less than or equal to p squared minus 9p minus 10. And then I need to solve this inequality, but you don't need to get involved in solving inequalities, even though it's possible here. You can factorize this. It's not hard to see. I need two numbers whose sum is minus 9 and the product is minus 10. So one of them would be minus 10, the other one would be minus 1. So I want to have this greater than or equal to 0. Am I right? By the way, let me not solve it in that way, because I am making things hard for myself. So let me do it in this way. Let me move 10 to the right. So I would say that p squared minus 9p is greater than or equal to 10, and I factor p out. It becomes p minus 9 greater than or equal to 10. Let me describe what I did. I moved minus 10 here, so it becomes positive 10 less than or equal to p squared minus 9p. So I shouldn't have moved this 10 from the beginning. Okay, I was thinking to solve this inequality, but it is not needed here. So, and then instead of writing 10 is smaller than this, I have written this is greater than 10. They are completely equivalent. Then I factored p out. I want to find the lowest order. So it means that I want to find the lowest value for p that satisfies this inequality. So you see that the first number that satisfies this inequality, as you said, is 10. If I put 1, 2, 3, this becomes negative. Multiply a negative number by a positive number is a negative number, and it cannot be greater than or equal to 10. So you see immediately that if I want to have this, I can of course choose p higher than this, but because the question is asking you about the lowest value, so I would say that from here I conclude that the minimum value is what? Is 10. Okay, and then if you plug 10 here, so it becomes 40 plus 5, it becomes 45, and q is greater than or equal to 45, so it is clear that the minimum would be 45. Yes, and that is exactly the full graph, I think. Yes, because if I ask you, I have 10 vertices and I want to make the q, the number of edges, minimum, but still I want to have this equality. Yes, 10 times 9 divided by 2 is 45. Yes, so it means that I need to put 10 vertices and draw the full graph, which of course is called the complete graph of order 10. If we have time, we will talk a little bit about these things. Okay, any questions so far? Okay, let us go to the next problem. These kinds of problems are also good. So you have practiced a little bit about this in your probably chemistry when you want to draw the isomers of different chemical compounds, yes? Let us do some exercises like this here. But of course, that is a particular type of graphs, which is called trees. We will come to them later. Draw a diagram for all simple graphs with vertex set A, B, and C. So you have 3 dots. One of them is called A, the other one is B, the other one is C. And then how many such simple graphs are there? If we do not consider the vertex names, how many different graphs of such, how many different types of such graphs do exist? Specify them. Yeah, that's a good exercise. Let us understand what does it mean. So I have 3 vertices. Let me call them. Let me name them for the first part of the problem. Yes? So this is A, this is B, this is C. That's it. This is a graph. This is a simple graph of order 3 without any edges. So this is one graph. Now consider graphs with one single edge. How many edges you can have at most for a simple graph with 3 vertices? It's clear. The fullest one is a triangle. So at most you can have 3 edges. This is the only one that you have without any edges. But for with one edge, how many with one edge I have? I can choose the edge here. I can choose the one edge to be here. And of course, I can choose the edge to be between B and C. So I don't think I hope that you agree with me there are no more with one edges. And now let us go with 2 edges. So I can choose A to B and A to C. This is one possibility. I can choose A to C with B to C. This is the second possibility. And then I can choose A to C, A to B, B to C. This is another possibility. I do not have any more, yes? And finally, I can have the fullest possible one, which is this triangle. So, if I ask you how many of them you see, 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 of them. The number is equal to 8. But now the important thing is actually usually the second part. So it means that you should think in a topological way. So it means that if a diagram can be obtained from another diagram by some kind of rotations, flipping and things like that, they shouldn't be counted more than once. Okay, so if I ask you how many graphs you see, by the way, I hope that you agree that this graph is different from that graph. Let us go to the abstract notion. Why these 2 graphs are not the same? If I consider the vertices, if I label the vertices, the reason is that if you remember, I told you graph is an ordered pair. If an ordered pair is supposed to be equal to another ordered pair, it means that the first components should be the same, the second components should also be the same. If I ask you what is the vertex set of this graph, of course you would say A, B, and C. If I ask you the same question for this, you will answer the same thing. So the first component means the vertex set of these 2 are exactly the same. But if I ask you what is the edge set of this, do you remember the convention? You write AB. But if I ask you what is the edge set of this one, it should be another set. Let me call it E prime. This would be EAC, and then you see that they are not equal. So technically speaking, these 2 graphs are not equal if we consider the labels, so I have to count them twice, and this one the third time. Okay, I hope that this is understandable. If not, please ask me. But now I want you to think about this. Let us remove all the labels. If I remove all the labels, how many graphs do you think will be left? How many different types of graphs we have?
Four.
Yeah, it is 4, exactly. I hope that you agree that if I remove these labels, there is no difference between a line segment and a dot in this way and in this way, because I can rotate, for example, this and make it like that. Yes, they are the same. And this one, so these fall into one category, so I will count them only once. Of course, this also should be counted once. And these 3 here and here only once, so up to here 3, and then here would be 4. So how many types? The number of types would be what we said, 1, 2, 3, 4. Yes. And there is nothing very special among these things. Counting this, you can use combinatorics, but counting this is much harder. Yeah, I would say it needs much more advanced mathematics, and it is algorithmically to be able to count this. If there is a formula, I don't remember exactly, but counting the number of graphs is very simple. Can you count this without writing them down and counting?
Which one of them?
No, all of them. I am asking you without drawing the graphs first and then counting like this 1, 2, 3, 4, 5, 6, 7, 8.
Not with the one with. We still have the labels, right?
Yes, yes. With the labels. Without labels is quite hard. If I don't remember, is there any algorithm to do that? Even if there is, that's not a very simple one.
Yeah, I was thinking about that one. That's a much harder problem. If we have labels, it's just 2 to the power p, I think.
No, no, that's a little bit. It's a coincidence here that 2 to the power p works here.
Because I was thinking like treating it like a binary number and toggling on and off.
No, no, that's not the case. Any other one? Can you think about this using combinatorics? For example, what is your guess about this? If I give you 4 vertices A, B, C, and D, and I ask you the same question, how many such simple graphs on 4 vertices you can construct, considering the labels?
Oh,
no.
Mr. Welbeck, isn't it 2 to the power of q?
No.
Ah, okay.
No. So let us. You see that it takes time, but I want you to think about this right now. If I have this, how many of these graphs I can construct using combinatorics? Not just drawing them first and then. And of course, I bet you will not want to do it by just drawing them. There are quite a lot actually. But do you have any idea? Do you have any strategy to count them?
Well, if we can calculate the maximum amount of lines, can't we do 2 to the power of that number?
Yes.
I mean.
Yes, that's correct. 2 to the power of p times p minus 1 divided by 2. So that's the answer.
That's what I.
Yeah, I told you are right. So 2 to the power of p times p minus 1 divided by 2 is the answer. And that's not hard because I told you that if you want to construct a graph, do you remember? What you need to do, for example, let us consider this scenario, which is simpler to write. What I do, I need to construct that abstract M set. Do you remember? So, sorry, let me just show you. Okay, you remember in the first session I was talking about this M set consisting of all 2 element subsets of V. Yes? Okay, so now if I ask you what is the set, what is this M set here? This is very simple to write. I want to write 2 element subsets. One of them is A, B, the other one is A and C, the other one is what? B and C. Okay? And then if I ask you how many pairs I can write here, you already know. You can say I have 3 elements, I want to choose 2 of them. So the elements here is choose 3, 2. Yes? But then for finding E, I need to make a subset of this. I have a set with 3 elements and I want to find the number of subsets, so it becomes 2 to the power of 3. Yes? Yeah, as simple as that. So the formula, if you want, let me write it here for you. So the number of them, it becomes 2 to the power of p times p minus 1 divided by 2. Yeah, please try to convince yourself later if you are interested in these kinds of problems. Okay, now The notion that I talked about here is a general concept in graph theory, and that is coming under the title of isomorphic graphs. Okay? What is the meaning of isomorphic graphs? You see, if I take the labels out, then I would say this graph is isomorphic to this graph. What does this mean? You understand that exactly. That's the notion. But two simple graphs are said to be isomorphic if it is possible to label the vertices of their diagrams such that the vertex sets and edge sets of the graphs become equal. Okay? If the idea is a little bit ambiguous, let me describe it here in this example 6. If I give you this pentagon and this star, of course geometrically they are completely different geometric shapes. Yes? But now I'm claiming that graph 1 and graph 2 are isomorphic. So in other words, if you consider these nails and if you consider these edges as rubber bands, without tearing these rubber bands up, you can detach these nails from the page or from the wood. Assume that you have put these nails in the wood. You can detach these nails and reorder the nails in a way that you make this pentagon. If this is going to happen, it means that the graphs are isomorphic. This is intuitively speaking, but strictly speaking, you need to do what the definition asks you to do. To start labeling one of them, and then labeling, so you can, let me not talk too much. So I would label the left one with any arbitrary letters. For example, let us consider this A, B, C, D, and E. So I just randomly label the vertices of one of them. But I start thinking wisely, if possible, to label the second one with the same letters. Okay? So that after labeling is done, the vertex sets and the edge sets becomes completely equal. Okay, for example, let me first of all you count them 1, 2, 3, 4, 5, because if the number of vertices are not the same, there is no hope for making them the same. If the number of edges are not the same, there is no hope. If I ask you how many edges are involved in this star, this would be, for example, 1, 2, 3, 4, and 5. So there are 5 edges, and in a pentagon we also have 5 edges. So from order point of view and from the size point of view, they match. So there are some possibilities for them to be isomorphic. Okay, now I start labeling them. So I label this A, but I label this one B, I label this one C, I label this one D, and then this E. Now let me ask you, if I ask you what is the vertex set of graph G1, clearly you say A, B, C, D, and E. If I ask you the same question now for graph G2, you will say the same thing, yes? Okay, so they are equal. Now let me ask you, what is the edge set of graph G1? Yes, one of them is AB. Yes, so let me cross it so that don't double count. Yes, so AB. The next one is BC. The next one is what? CD. And the next one is DE and EA. And now I am asking you the same question for EG2. So, do you agree that AB is one of them again? And then you agree that BC is another one. And then you see CD is another one. And then where is the other one? DE is the other one. And finally EA is the another one. Is there something left? No. So these are also equal. So from graph point of view, these two graphs are isomorphic. So if you consider only the relation between vertices, these two are equivalent in that way. Or from topological point of view, they doesn't differ, so you can change the other one without tearing up the rubber bands and change it to the other one. Okay, so is the idea of isomorphic clear? But it can be extremely hard to realize this. This is not very simple. And you don't need to be worried. I just want you to understand the concept. Okay, so please try your chance here. Do you think that these two graphs are isomorphic?
Yes.
Yes, they are isomorphic. So let me motivate you by this rubber band analogy. So if I take this nail and bring it out, then you agree with me, you will have the same situation. Now, do not look inside because there is nothing inside. What you see is a quadrilateral, and then you have one line like that. I hope that you understand from topological point of view there is no difference between that shape and this one, because you have a if I bring this out, then I will have this situation. I will have a diagonal here, and then I have this. So I have a quadrilateral with a diagonal and with an extra edge here. And if you see, this is essentially the same. This is how you convince yourself, but if you want to write it rigorously, you have to start labeling them. So I will, and then you will tell me the person who answered, who was it? I forgot. But let me write this. Let me write A here, for example. Randomly label this A, B, C, D, and E. Okay. Now I am asking you, the person who answered my question, who answered that they are isomorphic?
I did.
Okay, so may you please tell me what should I call this one in that case?
That should be called A.
A, and then now can you tell me what this should be called?
B.
It should be called B. And then, for example, let us jump here. What this should be called?
C.
It should be a C. Okay, good. And then what this should be called?
D.
D, and then finally this one has to be E. Yes, I think you are correct. But of course, if you want to convince yourself, let us do it very systematically. Here I have AB. Do I have AB here? Yes, let me cross it here. And then I have BC here. Do I have B and C connected here? Yes. Here I have B connected to E. Here I also have B connected to E. And then I have C connected to D here. So C connected to D. Everything's so far so good. And then I have C connected to E. Yes, I have C connected to E. And then finally I have D connected to E. So I have D connected to E. And then you see that nothing is left over here. Nothing is left over here. So definitely these are isomorphic graphs. Okay. Do you want a challenge now? Yes, I want to give you a little bit of time. Yes? Okay, you can answer now. So if you have your labeling in front of you, so let me start from somewhere and you tell me what to write, okay? So what do you put here?
E.
E. What you put here?
D.
Okay, sorry.
No, I said D.
D, okay. Like dog, okay. D.
Yes.
And then here?
That would be E.
E. Here?
Yes. That would be F.
F.
G.
G.
B.
B.
C.
C.
I.
I.
J,
J,
H,
H,
and A.
A. Okay, so this is the label that you are claiming is going to work. By the way, this labeling is not unique. For example, I found a different one. Okay, so let us check, by the way. Let us check one by one. Here on the right hand side I have A connected to B. Do you have this connection? Yes. You see A is connected to B in this labeling as well. Yes? Of course you should always count the number of vertices and the number of edges. I think these are simple things. If this is not the case, you immediately conclude they are not isomorphic at all. But if they are the same, there is still no guarantee that they are isomorphic. You have to be able to relabel them like that. Okay, so AB is correct. Then I go to, for example, BC. Let us check, is there any BC? Yes, I immediately see that BC is here. And then I have CD. Yes, I have CD here. And then I have DE, which is here. Yes, DE is also here, and EA is also here between A and E. You see this. Okay, and now let us go inside in this star now. Okay, so what do I have here? I have A to J, sorry. Yes, you have A to J here as well. And then you have B to G. Do you have, yes, B to G is here. Then we have C to I here. Yes, we have C to I here as well. And then we have D to H. D to H, yes, this is this arc, D to H. And then E to F. E to F. Yes, E to F. And then we go inside the star. So F to G. F to G, yes. And then G to H, yes, and then H to J, yes, J to I, yes, and I to F is arc, yes. Is there something left? No. Thank you very much. So we are done. So this shows that these two graphs are isomorphic. I don't know, how did you come to this way of thinking? Did you have a strategy for this or not?
I started with the center point as J, and then I went from that.
Okay, so my strategy is this. Usually I have practice. So my strategy is this. You see that I see a hexagon here, but apparently I don't see any hexagon there. Okay. So let me now, you learn this one, let me clean this one and then try to give my strategy to you. Okay, so I will clean this, and I have already done my labeling, so let me hopefully I haven't done any mistakes, otherwise it would be just a waste of time. Oops, no, I have to keep that. So I need to clean all the labels, yes, these dashes. Yes. Now, so what I saw that I have a hexagon here with 6 edges, but here I have a pentagon outside, and then of course this is also a pentagon. You have enough experience that a star is a pentagon. So I was trying to see if these two graphs are going to be isomorphic. I should be able to detect a hexagon there. So that was my motivation. So I realized this is a hexagon. Hexagon, yes? Do you understand? So from here to here, 1 edge, 2, 3, 4, 5, 6. And what I did, I just started randomly somewhere here in this hexagon. So I started putting a D here. Okay. And then you see that in this hexagon I go from D to H, so I wrote D to H here, and then you see what is the next coming, H to G, so I put this one G, and then I go from G to B, So you see, it is not hard. I'm just following my hexagon in both of them. Yes. And then after that, in this hexagon, I go B to A. So after that, I put A here, and then I go to E, and then of course I have to go to D, which is of course correct again. So this I made my hexagon. Okay, and then the rest becomes not very hard, because I would say, for example, here you see this vertex A is already connected to B and E. And there is one other connection left for me here. So, and you see A is connected to B and E, and what is extra is J. So I know that this should be J if this labeling is going to work. So let me just put J there. Okay? And then, for example, I do the same thing with this vertex G, for example. I see that G so far is connected to B and H. One more is left. And then I go here, I see that G is connected to B, that's correct. And this is connected to H, that is correct. But there is another one connected to G, and that is F. So it motivates me to put F here. Yes? And then I go, for example, to D. D is connected to H and E. There is a third vertex left, and I go here. D is connected to C, H, and E. So this missing vertex is C. Okay, everything is finished. What is left is in the middle one, and if you see, the middle one has to be I. And then you can check that this also works, hopefully, yes? So this is my strategy when I wanted to find this. You see, most of these connections I was able to detect by looking at this hexagon. Okay, is this a strategy understandable?
Yes.
Okay, good, good. Okay, so that is at this level. Don't worry about harder questions. So I just want you to know the notion of isomorphic graphs. Okay. Now, this is also something I want you to do yourself first. How many different types? When we say different types, it means that count them at the level of isomorphic graphs. So do not count the labeled graphs. Otherwise, I would say how many of them are there labeled graphs. I am just asking you about different types. And unfortunately, there is no simple closed formula for calculating the number of types. Okay, for the time being, I want you to do something for me and announce how many of them are there. Okay, so I want to give you 4 minutes. I think it's good. So you know what to do. Yes, I paused. Okay, so the time is over.
I found a couple of duplicates.
Anyone else? Any numbers?
I got 13 different types.
13. I think still you have duplicates. If I remember the number correctly. By the way, we can check the web. Anyone else? No opinion. If I remember correctly, yes?
Is it 7?
No. If I don't know. I because I did it long time back. I think if I remember correctly, there should be 11. Yeah, let us check. Okay. Let us check. So, I have 4 vertices. Okay, well, let us start a little bit systematically. So what I say is that without any edges. So how many of them are there? Only 1. So Q is 0. Let us consider the case that Q, the number of edges is 1. How many did you get here? if Q is 1? Do you have more than 1?
There's also the one with where it's diagonally.
No. Okay, but diagonally is the same. So might be this is one of your duplicates. So let me show you. Here, this is exactly the same here. Yes? Because, for example, I labeled them A, B, C, D, and I label this A, B, C, D. Then they are the same.
I found another duplicate and now I have 12.
Okay, so let us go one by one. Everybody agrees that if I want to keep up to our isomorphic graphs, there is only one type of simple graphs with 4 vertices and 1 edge. If you doubt about it, please ask me. But there is only one. Now let us go to 2 edges. And then I have 4 vertices. One scenario, of course, is this one and that one. One scenario is this one and, for example, this one. Do you think we have more?
No.
No. I hope that you agree with me. Is this a new one, do you think?
That's not a new one because we could swap the two.
Yeah, exactly. So which one is this? This is the second one. Do you agree, everyone? Okay, so it means that we are done with 2 edges. So far, how many of them are got? 1, 2, 3, and 4. Yes. Now let us go to 3 edges. Let us go to 3 edges. Q equals to 3. So let me just draw one of them. So one way is to this one. Do you agree? This is 1. The other one is this one. They are not isomorphic, are they? For example, you can see there is one vertex which is connected to 3 other vertices, but here we do not have any vertex connected to 3, so definitely this one and this one are not isomorphic, no doubts. But do you think there is another one as well or not? With 3 edges I am talking.
Yes, a triangle.
A triangle and a single point. Yes. A triangle, it doesn't matter which triangle. So one triangle and one single point. How many edges are there? There are 3. Okay, can you imagine more with 3 edges? Apparently not. Okay, so let us go to...
I have
yes?
another problem.
Yes?
It turns out I haven't the counted one, so now I regain the duplicate probably somewhere.
Okay, but do you agree with me that there are only 3 of them if I have 3 edges? But let us go to the 4 edges. So Q equals to 4. I have 4 vertices, 4 edges. Of course, one possibility is the famous square one. Yes, this is one possibility. Is there any other possibility? I can imagine that I have a triangle with 1 line. Okay, can you tell me, are there any more here with 4 edges? Let me draw one for you. Do you think that this is a duplicate or not?
That's a duplicate.
A duplicate of which one?
The first one.
Yeah, that's a square actually. Essentially, that's a square. If you just detach these 2 nails and swap them, you will get a square. Yes? So that's a duplicate. But can you imagine of something which is not a duplicate with 4 edges? I don't think so, yes? So let us go to number 5 edges. So Q equals to 5 edges. So let me just draw the simplest one, this one. Do I have more with 5 edges?
Yes.
Can you tell me how?
One where there's a cross and we will do one of the sides.
Okay, so let us do that. So that's also good to know. So you say cross like this and then what?
No, wait, maybe that's a duplicate. Because,
Yeah, that's a duplicate, isn't it?
yeah, okay. Yes.
So that's also a duplicate. Do you agree? This is the same. This is the same. If you see this one and this one, they are the same. Do you agree? Let us imagine it in this way. Detach it and put it here. You will get something like that. Yeah. So I don't know how to draw it, but you draw a quadrilateral 1, 2, 3, 4 with its diagonal. So that's exactly the same thing. Can I have more here? So how many have we so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, so my memory was working probably good. So the next one is also very simple. That's very yes.
I have a question. Why are you using Q5 if the order is 4 in the question?
No, the order is 4. Order means the number of vertices.
Oh, Q size.
Q is the size. So let me see, because I wanted to start systematically, otherwise I will lose track of. You see, I am saying that because you are telling me order is 4, it means that I have 4 vertices. The minimum value of the edges is not no edge at all, so it is 0. What is the maximum number of edges in a simple graph? Do you remember the formula we talked about today? It becomes 4 times 3 divided by 2 is 6. So it is clear that I should start from 0 up to at most 6. And then I am categorizing them to make sure that I am not ignoring some of them. Do you understand now?
Yes.
Okay, so when I write Q5, it means that I am concentrating only on 4 vertices. In all of them, I am considering 4 vertices, if you see. But the number of edges I am changing, so to be able to solve the problem a little bit systematically. That's the problem. And then there is only one graph with 6 edges. And that is the full graph. And if you doubt about it, please talk to me. Do you think that there is more than this for Q equals to 6 with 4 vertices? Okay, so now hopefully we are in an agreement, so the total number is 11. Yeah, please check web. I will also check it because I want to continue. If this is a very simple one, let me just finish this one. At least we add something new. Now we talk about the degree of a vertex. Okay, so let G be a simple graph or multigraph. It doesn't matter. And let V be a vertex of G. The number of edges incident with V is called the degree of V, and is denoted by this symbol. And if there is no matter of confusion, I just simply write degree of V. By definition, every loop, this is important, contributes 2 to the degree of the corresponding vertex. The maximum degree and the minimum degree of a graph are denoted by delta, capital delta and small delta respectively. So in principle, degree, if I ask you what is the degree of this vertex, you draw a small circle around that and see how many edges are going out. So it is 3. Yes? So the degree of this one is 2. As simple as that. If I ask you what is delta in this graph, it means that I am asking you about the maximum degree, which evidently in this graph is 3. And if I ask you what is delta, small delta, it means that the minimum degree, and that is 2 in this case. So that's very simple. And there are some words, terminologies that you need to know. Let G be a simple or multigraph, and let V be a vertex of G. Then V is called an odd vertex if its degree is odd. If it is called an even vertex if its degree is even. It's called an isolated vertex if its degree is 0, and it is called a leaf or a pendant if its degree is 1. And by the way, this spelling is correct, so if you write the pronunciation of this pendant and this pendant are exactly the same, that more or less they are the same thing, but this pendant means a piece of jewel that you hang it, I don't know, through a necklace. So in graph theory, this is pendant. The pronunciations are, I think, identical. Okay, and let us do this one, and then we are done. Consider the following graphs in this figure. Determine the order and size of this graph. This is just repetition. So what is the order? Order is the number of vertices, so I count them: A, B, C, D, E, F, G. So how many of them? 7. And if I ask you the size, what is the size? So this is 1 edge, 2 edge, 3, loop is the 4th one, 5, 6, 7. So that's also 7. Okay, so determine the degree of all vertices. So what I can write, for example, if I ask you what is the degree of A, the degree of A is simply 1, 2, 3. If you draw a small circle around that, you will see that there are 3 edges coming out or coming in. It doesn't matter. So degree of A is 3. Degree of B, what is degree of B? 1, 2, 3, 4. If you doubt about it, please talk to me. And what is degree of C? This is the only problem that you need to be careful. So if that's the same story, I draw a circle around that, and then you see that I have 3, 1. According to definition, every loop contributes 2 to the degree. So even though I have 2 edges, but according to that definition, when I ask you about the degree here and 3, and that is reasonable, yes, because the same strategy, I have 3. So the degree of C is not 2, be careful. This is the only problematic one. So that is 3, and then the degree of CD is 1, the degree of E is 0, yes, the degree of the degree of F is 2, and the degree of G is 1. Okay, and then which vertices are odd? So A is odd, D is odd, C is odd, I don't know, G is odd. Which one are even? You can immediately see which one is isolated. Only E is isolated. The degree is 0. Which vertices are leaves or pendants? You say G and D. These are of degree 1. Determine the capital delta and little delta. Capital delta is 4 and a small delta is 0.